Okay, welcome to class. So this lecture, we will be talking about boundary value problems. Some logistics. Wednesday, we will not have class. And on Friday, we will have midterm 2. Wednesday, technically, we don't have class. But how many of you will come to class if I were to host a midterm review? Please raise your hand. Okay. And look for the announcement. So this class, we'll be talking about boundary value problems. Previously, when we have an ODE, we have talked about how to solve for the general solution for first order ODEs, second order of ODEs, and then coupled system of ODEs. And after we have a general solution to get the particular solution, we need to specify initial conditions. And for nth order ODEs, we will require n initial conditions. So this is a general form of an nth order ODE, starting with n. And we will need n initial conditions in order to solve for a particular solution. But what if we don't specify the initial condition at 0, and we specify the initial and final points, or the boundary values? And similarly, if for nth order ODEs, it will require n boundary conditions, similar as n initial conditions. And there are a lot of flexibilities in defining these boundary conditions. So if you think about the initial conditions, you can think of it as you have a time t and you have initial point at 0. And you might know the initial point, y of 0, and you might also know the initial slope, y prime of 0. But for the boundary value problem, so say this is a second order ODE, so you have 2 initial conditions. But for boundary value problems, you can constrain 2 points. At the left, you might have a y0, and the right, you might have a y of L. So both of these have 2 points, and they will constrain the ODE solution. And by flexibility, I mean that there are a lot of different types of boundary conditions. And from now on, I'll call boundary conditions BC. There are simple boundary conditions where the boundary conditions are constant, and these will be things that we will be able to solve analytically. There are type 1 condition where we specify the function values, the original function's value at both boundaries. For example, it's given y of 0 and y of L. So as an example, I can have y of 0 is equal to 3, and y of L is equal to minus 2.5. And those will be the type 1 boundary conditions. And you can think of it as when you have an interval x, and when x is equal to 0 at the left boundary and x equals to L at the right boundary, we know the function's point, y of 0, and then the function's point, y of L. We also have type 2 boundary conditions where we specify the first derivative at both the boundaries. So for example, we can know y prime of 0 equals to a constant, and then y of L equals to some other constant. For this, you can think of similarly on an interval x. When x is equal to 0, we don't know the point, but we know the slope of the point. So y prime of 0. And on the right, x equals to L, we also don't know the point, but we know the slope at that point. So y prime of L. As you could imagine, we can also mix match the function and the first derivative. So if we specify the function value at one end and the first derivative at the other end, we have a mixed boundary condition. So for example, I have 2 intervals. So for this interval, I know the function value at the left end and know the slope at the right end. Or you can also know the slope at the left end and know the function value at the right end. So these are mixed boundary conditions if they equal to some constant. But we could also have some more complicated boundary conditions, where boundary conditions are complicated functions instead of constants. So that's called a Robin type 3 condition, where the boundary condition at least one of the end is a function. So for example, I can have y of 0 plus y prime of 0 plus 2 is equal to 0. And this is at the left boundary because it's a function evaluated at 0. This is a Robin type 3 condition because you cannot rewritten it as y0 is equal to some constant or y prime of 0 is equal to some constant. So this whole thing is a more complicated function of f of y of 0 and then y prime of 0. And similarly, you can do something with the right boundary condition. You have maybe 2 y of L plus sine of y prime of 0 of L plus 3 is equal to 0. You can't rewrite this into some constant form. So this is a more complicated function and therefore a type 3 condition. And usually we will need to solve this in Python. Any questions? Okay. Let's try identifying some of the boundary conditions, whether it's type 1, which is knowing the original values, or type 2, the derivative, mixed for the original value or first derivative, or complicated functions. Complicated. Okay, so for the first one, we have these are all equal to constant, so it's not type 3, not complicated functions. And we have the original function, so this is a type 1 boundary condition. For the second one, these are all equal to constant, so not type 3. This is a first derivative and then original function, so it's a mixed match, so this is mixed. For the third one, this is a constant first derivative, and this one, can we rewrite it in terms of a constant? So we can rewrite this as y prime of L is equal to 20, so this is a constant. So first derivative, so this is a type 2 boundary condition. The fourth one, we have original function and first derivative equal to constant, so this is a mixed boundary condition. For the fifth one, can we rewrite this into a constant form? So y prime of 0 is equal to -5. And then this is first derivative, original function, so mixed boundary condition. The sixth one, can we rewrite this as a constant? No, we cannot. So this is a more complicated function. So if one of these has a complicated function, it's automatically a type 3 boundary condition, regardless of the other one. Okay, and for the seventh one, we have a first derivative equals to a constant and then a complicated function. So this should be a type 3 boundary condition. Okay, any questions? Okay, so now we identified 4 different types of boundary conditions. We can also look at the homogeneity of the boundary value problems. So previously, for second order ODE, we have a general form. When we know that g of x is equal to 0, it is homogeneous. And when it's not equal to 0, it's not homogeneous. And similarly, for boundary value problem, we can also define that with an extra condition. So first, we look at g of 0 if it's equal to 0. If it is equal to 0, we also look at if all the boundary conditions will equal to 0. So that means that we have to have y of 0 is equal to 0 and y of L is equal to 0 for type 1 boundary condition. And for type 2 boundary condition, we need y prime of 0. So everything equal to 0 for type 2. And if you have a mixed boundary condition, you will have y prime of 0 is equal to 0, y of L is equal to 0, or y of 0 is equal to 0, y prime of L is equal to 0. So I'm just listing all the possible things, but you have to note that all the boundary conditions have to be equal to 0 in order for it to be homogeneous. And it's easy to be non-homogeneous because it's defined as not homogeneous. So if it doesn't satisfy all these, it's not homogeneous. Okay, so let's try these problems. Yes. So the question was, if g of x is equal to 0, but one of the boundary condition is not equal to 0, would that be classified as a homogeneous or non-homogeneous boundary value problem. So this is a non-homogeneous boundary value problem because it has to be g of x equal to 0. So this satisfies, but all the boundary conditions has equal to 0. So this doesn't satisfy. So this is yes and no. And then if you do an and, this is no. So not homogeneous. Great question. And so we have to distinguish if the ODE is homogeneous and if the boundary conditions is homogeneous. And this is homogeneous ODE, but non-homogeneous boundary condition, and therefore leading to a non-homogeneous boundary value problem. Okay, so here are more practices. So identify if it's homogeneous or non-homogeneous. So first we look at the ODE. Does it have a non-homogeneous component? So this is g of x is equal to 2, which is not equal to 0. So it's a non-homogeneous ODE. So it's automatically non-homogeneous BVP. So this is non-homogeneous BVP because it's non-homogeneous ODE, but are the boundary conditions homogeneous? Yes. So it's homogeneous boundary value problem, boundary conditions, but a non-homogeneous BVP. Okay. Any questions here? So the second problem, so g of x is equal to 0. So we have a homogeneous ODE. And then for the boundary conditions, we have equal to 0, equal to 0. So this is also a homogeneous boundary condition. So because they're all homogeneous, we have a homogeneous boundary value problem. The third one, we have g of x is equal to 0. So homogeneous ODE. For the boundary conditions, it's equal to 0, equal to 0, so homogeneous. So we have a homogeneous BVP. So compare and contrast 2 and 3. Even though we have different types of boundary conditions, so this is original functions, type 1, and this is first derivative, original function, mixed. Regardless of their types, if they're all equal to 0, they're homogeneous. So it doesn't matter what type they are. Okay, for the fourth one, we have g of x is equal to sin of x. So we have a non-homogeneous ODE. So it's automatically non-homogeneous BVP. And the boundary conditions, because they are equal to 0, they are homogeneous. The fifth one, we have g of x is equal to 0. So we have a homogeneous ODE. Here, this is equal to 0, but this can be written as y of l is equal to -4, which is not equal to 0. So we have a non-homogeneous BC, so we have a non-homogeneous BVP. The sixth one, g of x is equal to 0. The boundary values are equal to 0, so this is a homogeneous BVP. Any questions? So we went over the types of boundary conditions and the homogeneity of boundary value problems. So now we should be able to start looking at how do we solve boundary value problems. So how do we solve boundary value problem? It's only different in the case when we substitute to find the particular solution. So what's the same as before is to solve for the general solution, very similar to the initial value problem. So we first want to find the general solution. So for this ODE, how do we find the general solution? We first look at its characteristic polynomial. So lambda square plus 4 equal to 0, because this is y prime plus 0 y double prime plus 0 y prime plus 2 4y. So this is lambda squared plus 4 is equal to 0. And then solve for lambda, we have lambda is equal to -4, lambda is equal to plus or minus 4, 2i. And therefore, the general solution will be y of x is equal to c1 sine of 2x plus c2 cosine of 2x. This is no different than the initial condition. The second step is to actually solving the BVP by substituting. So we have the boundary condition. So first, this is the original function. So this is a type 1 boundary condition, and it's non-homogeneous. So if we substitute y of 0 is equal to -2, so from all the x's here, I substitute 0. So c1 sine of 0 plus c2 cosine of 0. Sine of 0 is 0, cosine of 0 is 1. So we have -2 is equal to c2. So this is left. And for the right boundary condition, we have y of pi over 4 is equal to 10. And for all the x's here, I substitute pi over 4. So c1 sine of pi over 2 plus c2 cosine of pi over 2. Okay? And I don't remember what this is, so let's draw a sign. So this is 0, pi over 2, so this is 1. And for cosine, this is 0. Okay, so 10 is equal to c1 plus 0. So now we solve for c1 and c2, and the third one is to write the solution by substituting the c1 and c2. So y of x is equal to c1, which we solve as 10 sine of 2x, plus c2 we solve as -2. So -2 cosine 2x. And now we have solved for the boundary value problem. Yes. With both. Yes. Yes. It's because we have a 2. So 2 times that is, yeah. Any other questions? Okay, so in this case, we found that the boundary value problem has one unique solution. But that will not always be the case. For example, let's consider the same ODE, but let's change up the boundary condition a little bit. So same ODE, but I changed the boundary values. So first, we solve for the general solution, which we already solved. So lambda is equal to plus or minus 2i. So the general solution is c1 sine of 2x plus c2 cosine of 2x. Second step, substitute the boundary conditions. So y of 0 is equal to -2. And for all the x's, I substitute 0. So c1 sine of 0 plus c2 cosine of 0. Sine of 0 is 0, cosine of 0 is 1. So we have -2 is equal to c2, same as before. So this is left. And for the right one, we have y of 2 pi is equal to -2. So I substitute all the x's here as 2 pi. So we have c1 sine of 4 pi plus c2 cosine of 4 pi. Okay, and then for sine of 4 pi, this is equal to 0. Cosine of 4 pi, I believe, is equal to 1. So we have -2 is equal to c2. And if we look at what we found from these two boundary conditions, they all tell us the same thing, that c2 is equal to -2. But what about c1? It doesn't tell us what c1 is. So if we substitute back and get the solution, we found that y of x is equal to c1. We don't know c1, so we keep writing c1 sine of 2x plus c2, which is -2. So -2 cosine of 2x. So this is our final solution. And we found that this solution has a constant here that should be real. And so we have infinitely many solutions. So we can do c1 is equal to 0, 1, 1.5, minus pi, whatever. So we have infinitely many solutions in this case because these two boundary conditions only constrain one of the constant, but not the other. Any questions? Okay, so far we have seen we have one unique solution, infinitely many solutions, and as you could expect, we could also have no solution. So let's try with the same ODE, but another different boundary values. So we have first general solution, we already know, which is C1 sine of 2x plus C2 cosine of 2x. And then second step, we look at the boundary conditions. So y of 0 is equal to -2. Substitute. So we have C1 sine of 0 plus C2 cosine of 0. This is 0, this is 1, all the same as before. This is left. And for the right boundary condition, we have y of 2 pi is equal to 3. So we have C1 sine of 4 pi plus C2 cosine of 4 pi. So this is 0, this is 1. So we have 3 is equal to C2. And what does the two boundary conditions tell us? They tell us that different things. So C2 is equal to -2 and C2 equals to 3. But that couldn't be true. Because there is a contradiction, this tells us there is no solution to the boundary value problem. Okay. If ever there's a contradiction between the two boundary conditions, it tells us that there will be no solution to such boundary value problem. So as you see, for the same ODE with different boundary conditions, we could have one unique solution, infinitely many solutions, or no solution. Okay, any questions? So now we have demonstrated all the possibilities. Let's try more practice problems. So solve this ODE and subject it to some boundary conditions. So let's first see what are the types. So this is original function. So this is type 1 boundary condition. This is a homogeneous ODE, but a non-homogeneous boundary condition. And therefore, this is a non-homogeneous boundary value problem. So first step, to find the general solution, we have lambda squared plus 3 is equal to 0, because we have a plus a 0 y prime here. So lambda squared is -3, lambda is plus or minus square root of 3. So the general solution would be y of x is equal to C1 sine of square root of 3x plus C2 cosine of square root of 3x. Okay. Second step is to look at the boundary conditions. So the left boundary condition tells us that y of 0 is equal to 7. I substitute 0 to all of them. So C1 sine of 0 plus C2 cosine of 0. So this is 0, this is 1. We have 7 is equal to C2. For the right boundary condition, we have y of 2 pi is equal to 0. So C1 sine of square root of 3, 2 pi, plus C2 cosine square root of 3, 2 pi. Okay, I actually don't know what square root of 3, 2 pi is. Interesting. Okay, let's try. If we don't know this, let's look at Desmos. Cosine square root of 3, 2 pi. Okay, so this is some number. So let's just leave it there. It's way too complicated. Okay, so I think I did the problem. This shouldn't be 2, I think. So this, if we were given this type of problem, we'll need to substitute C2 inside here. So we have 0 is equal to C1 sine of square root of 3, 2 pi, plus 7 cosine of square root of 3, 2 pi. And we can solve for C1. So make this to the left, minus 7 cosine square root of 3, 2 pi, divided by sine of square root of 3, 2 pi. And then you can further simplify this. I think this is cosine divided by sine. This is minus 7 cotangent square root of 3, 2 pi. Okay, so we have C2 is equal to some constant, and then C1 is equal to some really complicated constant. But they are all constants, so we can substitute them back. So 3, we have y of x is equal to C1, which is this whole thing, minus 7 cotangent square root of 3, 2 pi. Nothing to be scared of. This is just constant. You can put it in decimals. And then sine of square root of 3x. And then plus C2, which is 7, times cosine square root of 3x. And this is our final solution. And it is an unique solution. Any question? Okay, another practice problem. So solve this BVP. So this is y double prime plus 0y prime plus 25y. So we have general solution. We have lambda squared plus 25 is equal to 0. So lambda should be equal to plus or minus 5i. So the general solution would be C1 sine of 5x plus C2 sine of 5x. No, cosine of 5x. Okay, and the second one, we look at boundary conditions. So for the left boundary condition, we have, so here we have first derivative, so this is type 2 boundary condition. And these are non-zero, so non-homogeneous boundary condition, homogeneous ODE, so non-homogeneous boundary value problem. So y prime of 0 is equal to 6. But what is y prime? So let's take the derivative of this. So y prime of x is equal to chain rule, so 5c1 cosine of 5x plus chain rule. So this is a negative sign, so negative 5c2 sine of 5x. So if we look at the left boundary condition and substitute 0 into all the first derivative, we have 5c1 cosine of 0 minus 5c2 sine of 0. Sine of 0 is 0, cosine of 0 is 1. So we have 6 is equal to 5c1. C1 is equal to 6 minus divided by 5. For the right boundary condition, we have y prime of pi is equal to minus 9. And this should be equal to 5 times C1 cosine of 5 pi minus 5 times C2 sine of 5 pi. Okay, and what is 5 pi? Let's see. So this is sine, this is cosine. For cosine 5 pi is equivalent to 5c1 cosine of pi minus 5c2 sine of pi. And cosine of pi is here, minus 1. Sine of pi is here, 0. So this tells us that it should be minus 9 is equal to minus 5c1 minus 0. So c1 should be equal to 9 divided by 5. If you look at the boundary conditions, they're telling us two different things. C1 is equal to 6 divided by 5 or 9 divided by 5. And it's a contradiction. And therefore, there is no solution to the boundary value problem. Any question? Okay, more complicated one. This time we have a non-homogeneous ODE subjected to non-homogeneous conditions. And this is first derivative, original function, so this is a mixed condition. And here I have given you already the general solution. You should be able to do this on your midterm. So this is the homogeneous part, and this is the particular part, whether you solve it with variation of parameters or method of undetermined coefficient. you should know both methods. Okay, so this is the first step, already given the general solution. The second step is to substitute the boundary values. So we have first derivative, so why don't we just first take the first derivative of the general solution? So chain rule, we have 3 minus 3 C1 sine of 3x plus 3 C2 cosine of 3x plus, so cosine should be minus sine, so sine of x minus 1/8. So let's look at the left boundary condition. We have y prime of 0 is equal to 5. So I substitute everything here as 0. So minus 3 C1 sine of 0 plus 3 C2 cosine of 0 minus 1/8 sine of 0. Sine of 0 is 0. Cosine of 0 is 1. So we have 5 is equal to 3 C2. And therefore C2 is equal to 5 divided by 3. Right boundary condition, we have y, the original function at pi over 2 is equal to minus 5 over 3. So I will substitute the original general solution x as pi over 2. So C1 cosine 3 divided by 2 pi plus C2 sine 3 divided by 2 pi plus 1/8 cosine 3 divided by 2 pi. And then to simplify this, again, I don't know everything, so I'll just draw it out. This cosine, this is sine. So at 3 over 2 pi, this is 1.5 pi, so it should be here. So sine should be equal to minus 1, cosine should be equal to 0. So this tells us minus 5 divided by 3 is equal to minus C2. And therefore C2 is equal to 5 over 3. And so these two boundary conditions tells us the same thing, that C2 is equal to 5 divided by 3, but tells us nothing about C1. So C1 remains a constant, that's a real constant. So we substitute these constants back to the general solution. We have y of x is equal to C1, which is still a constant. So C1 cosine of 3x plus C2, which is, we found 5 divided by 3, sine of x, sine of 3x, plus, there's no constant here. This is a particular solution, 1/8 cosine x. So this is our final solution. Because we have a constant, we have infinitely many solutions. Any question? Okay, another one. So here we have a homogeneous ODE and homogeneous boundary conditions. So we have a homogeneous BVP. We have original functions, so this is type 1 condition. To solve this, let's solve for the ODE. So the general solution, this is the same as before. So lambda squared plus 4 is equal to 0. So lambda is equal to plus minus 2i. So the general solution should be C1 sine of 2x plus C2 cosine 2x. Second step, look at the boundary conditions. On the left, we have y of 0 is equal to 0. Substitute this in, we have C1 sine of 0 plus C2 cosine of 0. Sine of 0 is 0, cosine 0 is 1. So we have 0 is C2. The right boundary condition is y of 2 pi is equal to 0. So C1 sine of 4 pi plus C2 cosine of 4 pi. Sine of 4 pi is equal to sine of 0, which is 0. Cosine 4 pi is equal to cosine of 0, which is 1. So 0 is equal to C2. Okay, so these two tells us the same thing, that C2 is equal to 0, and tells us nothing about C1. So C1 is real. constant. So substitute back in, we have y of x. C1 is a constant, C1 sine of 2x, plus C2, which is 0. So everything about the cosine is gone. So this is our final solution. Because we have a constant, we have infinitely many solutions. Okay. I think this is the last one. So solve for the BVP, this one. So this is homogeneous, homogeneous, homogeneous. This is homogeneous boundary value problem. This is original function, so type 1 condition. To find the general solution, this is lambda squared plus 3 is equal to 0. Lambda is equal to plus or minus square root of 3i. So the general solution is C1 sine of square root of x, 3x, plus C2 cosine square root of 3x. Okay. Evaluate the boundary conditions on the left. We have y of 0 is equal to 0. As you all know, this is 0, this is 1, so this is equal to C2. On the right, we have y 2 pi is equal to 0. And then 2 pi, sine of 2 pi is 1. And then cosine of 2 pi is 0. Wait, sine of 2 pi is 0. Let's write it out. So square root of 3, 2 pi plus C2 cosine square root of 3, 2 pi. Okay, and C2 is equal to 0. Substitute here, so we have 0 is equal to C1 sine of square root of 3, 2 pi. And then so C1 is, we move this to the left, we have 0. So these two tells us that C2 is equal to 0, C1 is equal to 0. So if we substitute back in, we have y of x is equal to 0 plus 0, which is 0. If we have a solution that is y of x is equal to 0, this is called a trivial solution. And this is one unique trivial solution. Any question? Okay, so these are the boundary value problems. Any questions on how to identify the types, identifying homogeneity, and then substituting and finding the boundary conditions? Okay, no questions. Awesome. So this is the lecture part, but I could stay a little longer, 10 minutes to go over the lab. Last time, I think in the lab 8, we have some practice problems. So I can go over the solution of those because there will not be a solution manual, so I can go over it now. Okay, why don't we do let's do this. Let's do this problem. Rewrite into a system of these. All these problems are really important. I'm telling you on Friday. So please do check them out. So this problem, we have a higher order ODE. And this is non-homogeneous. We want to write it into a system of first order ODEs. And the way we do that is to first define auxiliary variables. And the number of auxiliary variables should equal to the order of the ODE. So identify the order. This is first, second, third, fourth, sixth. So this is a 6th order ODE. So we should have 6 auxiliary variables. So let's define W0 as y, the original function, W1 first derivative, W2 second derivative, W3 third derivative, etc. And W5 fifth derivative. So we have from 0 to 5, so 6 auxiliary variables. The second step is to take derivative of the auxiliary variable and rewrite it in terms of auxiliary variables. So take the derivative, so W0 prime is y's derivative, and y derivative we define it as W1. So W1 derivative is y prime's prime, so we define it as W2. W2 prime is y double prime's derivative, so y triple prime, we define it as W3. W3 prime, I think you have seen the trend. So 0 prime is 1, 1 prime is 2, 2 prime is 3, 3 prime should equal to 4. So this is y to the 4th. And then W4 prime is equal to y fifth order derivative, which is y fifth. But at the end, y5's derivative, we have y to the 6th order derivative. But we don't have an auxiliary variable defined for y 6th order derivative. So we need to look at the original ODE and rewrite it in terms of y6. So to rewrite it, we have y to the 6th is equal to bringing everything here to the right. So we have sine of y prime minus 6 y 4 minus 4 y triple prime plus 8 y double prime plus becomes a minus y prime plus 2y minus 10e to the x. And then we have a 2, so we divided by everything on the right by 2. So 1/2 divided 6 divided by 2 is 3. 4 divided by 2 is 2. 8 divided by 2 is 4. So minus 1/2. So 2 divided by 2 is 1. 10 divided by 2 is 5. So we have rewritten the original ODE as this. But we want to rewrite it in terms of auxiliary variable W. So we'll just need to substitute all the y's here in terms of W. So we have 1/2 sine of y prime. Y prime is defined as W1 minus 3 y to the 4th. So this is W4 minus 2 y triple prime, W3 plus 4 y double prime, W2 minus 1/2 y prime. This is W1. And then plus y is W0 minus 5e to the x. Okay, so now we have a system of first order ODEs. If we erase all the y's here, and we leave it only in terms of W, these are the system of first order ODEs that we want. Any question? So this is how we rewrite higher order ODEs into a system of first order ODEs. And if I ask you, well, how do we write this in terms of Python if I want to write it into solve ODE, solve IVP? How do you write this as a system of ODEs? How do we do that? So we can, for each of these, we define a lambda function, and then we finally assemble an ODE lambda function. So to write it in terms of Python, we have dw0 dt is equal to a lambda function of independent variable t or x, doesn't matter. And then all the dependent variables. So dependent variable in this case are 0, 1, 2, 3, 4, 5. So W0, W1, W2, W3, so on. Okay, and then colon, and then it's defined as W1, so W1. And then I'll just copy and paste this. Let's see, how do I copy and paste? Copy and paste this for 5 times. So what has changed? It's important that in coding, we always copy and paste, but it's difficult to know what should we change. That's what's important. So if we look at dw1 dt, so we change here. The variable name is dw1 dt. The variable stays the same. And on the right, we have w2. So instead of w1, we have w2. And so on. So here should be dw dw2 dt is equal to w3. And then dw3 dt is equal to w4. And then dw4 dt is equal to w5. And the different thing will be dw5 dt is equal to, so this thing still is here, the same, okay? And here we want to type everything here inside the function. So after the lambda function, we have 1/2 np. If you write np here, it will give a syntax error because you want to multiply. So 1 divided by 2 times np dot sign of w1. So these are Python syntax. It counts. If you don't write the star here, you'll give a syntax error. So -3 times w4 -2 times w3 plus 4 times w2 -1 divided by 2 times w1 plus w0 -5 times e. So for e, you can either write np dot exp, so exponent of x. Or alternatively, you could also do -5 times np dot e, natural number, raised to the power of, so 2 stars of x. Okay, any questions? And these are hard examples. And if you can do the hard examples, you can do the easy ones on the exam. So here I also have 2 other ones. You can write this in terms of the lambda functions. Let's also look at this one. It's a reverse problem. So given the code, can we write it as a math function? So the system here is dw1 dt. So w1 prime is equal to the lambda function of t plus w1 raised to the power of 2 minus w2. And the second one gives w2 prime is equal to w2 raised to the power of 2 minus w1. And that's the mathematical form. Okay, and lastly, in one sentence, suggest how to fix the following codes that were supposed to be the definition of system of ODEs for inputting to solve MVP. It gives a type error when running these lines. So when we see type error, so these are the definition of time, giving the empty W1 and W2, these are fine. But if we have a type error, we want to look at the definition of the functions. So here, usually when we define it as functions, we need the lambda statement as define it as lambda function. But here, it directly defines it as t plus w1 raised to the power of 2 minus w2. It's not a function. It takes in this lint space array and the zeros array and then performs operation. So the final result of dw1 dt is an array and not a function. So to fix this, so in one sentence, suggest how to fix. I would say that make dw1 dt, dw2 dt, and ODE system as a lambda function instead of using directly these variables. And that should fix the problems. Any question? Okay. This is this lecture, and I'll see you hopefully on Wednesday. See announcement.